Hey everybody, welcome back to chemistry. And so today what I want to talk about is a bit about the atomic theory. So first the thing I want to do is talk about some of the data that was available back in the late 1790s and 1810s that allowed the atomic theory to be developed. Then I'm going to talk about the four postulates of the atomic theory, and I'm going to talk about the fact that for the most part the atomic theory is correct, but there are some things that are not quite right with it, and you need to know those differences between what we thought the atoms were doing back when the atomic theory was developed versus what we think the atoms are doing now. And so this is all covered in section 2.2 of your book. So the atomic theory was developed by a guy named John Dalton, and he was an English school teacher and amateur scientist, and he really embraced the idea that all matter is comprised of atoms. But he went further than that. He said, okay, all matter is comprised of atoms, but I want to develop a whole theory behind that. And so a theory, as you might remember, is used to explain data. So this theory that he developed was used to explain a lot of data. So I need to talk a little bit about what this data was. So by the time John Dalton developed his theory in 1808, there was a lot of quantitative data in chemistry. And so very importantly, at that time, we knew that there were a lot of different compounds out there, but we also knew what masses of elements were in the compound. So that was very important. And another thing we knew is that we knew the masses of compounds before a reaction and after the reaction, so we were able to compare those two. So from this data, some other people put together some laws to explain all this data. And so one law is called the law of definite proportions. I'll talk about that next. Then there was the law of conservation of mass, and then there was the law of multiple proportions. So let me talk a little bit about the law of definite proportions. So the law of definite proportions is also called the law of constant composition, and sometimes you'll hear it called the law of constant proportions or the law of definite composition. So all those are possible. So we're going to call it the law of definite proportions. And so the law says all samples of a given compound, regardless of their source or how they are prepared or how much you have the same proportion by mass of their constituent elements. So there are kind of two important aspects of this. One important aspect is that the percent elemental composition by mass is always the same for that compound, however you obtain a sample of it. So for example, let's say you get some sodium chloride from Kentucky, and let's say you get some sodium chloride from Antarctica, or let's say you get some sodium chloride from anywhere else in the world. What we now know is that wherever you get the sample of sodium chloride, it has the same composition of the elements by mass. And so there are two elements in sodium chloride, and they are sodium and chlorine. So no matter where the sample is from, you have always 39.3% sodium and 60.7% chlorine. Now, if you take those numbers, the 60.7% chlorine, and divide it by the 39.3% sodium, you get a proportion there. So you get 1.54. That is the ratio of the mass of chlorine to sodium. And again, wherever you get a sample of sodium chloride throughout the world, the ratio of the mass of chlorine to sodium will always be 1.54. And another sort of thing related to this, it doesn't matter how much sample of sodium chloride you have. You always will have that same mass ratio of chlorine to sodium being at 1.54. So for example, let's say you had 100 grams of sodium chloride and you did an elemental analysis of this sample, and you would find that in the 100 grams of sodium chloride, there are 39.3 grams of sodium and 60.7 grams of chlorine. So when you divide those two numbers, you get that definite proportion of 1.54. Now, if you had double the sodium chloride, you would double the masses of sodium and chlorine you would have, but because you're dividing the two numbers together, you would have the same proportion of chlorine to sodium at 1.54. And if you take any mass of sodium chloride, it could be for example, 58.44 grams, you would have proportionate amounts of sodium and chlorine such that when you divide those two numbers, you get 1.54. So you can see that that proportion of the elements is not changing no matter where you get the sample from or how much of the sample you have. And so this is true for all compounds. It's just that other compounds will have different elements at different proportions. Okay, so now there was another sort of law that I want to talk about, which is sort of summary of the data that John Dalton was looking at. And so this is the law of conservation of mass. And basically this law was developed in the late 1780s. So what this law basically says is that whenever you have a chemical reaction of any kind, if you take the mass of all the reactants, you will find that that mass is exactly the same as the mass of all the products. So we have sort of a nice example of that here. So here we're reacting elemental sodium with elemental chlorine, and then when you carry out the reaction, it's a pretty exothermic reaction. It releases a lot of heat, and you have those two elements of sodium and chlorine lose their properties and become something new with new properties, which would be sodium chloride, which is table salt. So if you were able to measure the mass of the products after that reaction, the table salt, what you would see would be exactly the same as the mass of the reactants before it. So another way to think about this is as follows. If you have as much mass or matter after the reaction as you do have before the reaction, what that means is that you're not having any extra matter coming out of somewhere and appearing in the products. So matter cannot be created. Also, it's not like when you have the products, you would have less there, like matter was just somehow disappearing. So matter is not being destroyed. And so this law applies to all chemical reactions. Okay, so now a little bit trickier law to go through is called the law of multiple proportions. And so this was another piece of information that John Dalton was considering when he was thinking of his atomic theory, and he actually thought of the law of multiple proportions. So I think maybe the best way to describe that to you is for me to go over a specific example of the law. So here, let's imagine two elements. Let's say we have element A, which is carbon, and element B, which is oxygen. So what will happen is that you can get two compounds from these two elements. So in one case, you can get one carbon atom binding to one oxygen atom, and it'll form carbon monoxide. Now, let's say you were able to weigh out the oxygen that is bound to carbon in this compound. What you would find is that for every 1 gram of carbon, you have 1.33 grams of oxygen bound. And again, this is because carbon monoxide has one atom of oxygen bound to one atom carbon, and as you might imagine, the oxygen is a little bit heavier. Now, let's say you're looking at another compound formed by carbon and oxygen, and this compound is carbon dioxide. So if you were able to get the mass of the elements of that compound, what you would see is that for every 1 gram of carbon, you don't have 1.33 grams of oxygen like you have in carbon monoxide. You have 2.67 grams of oxygen in that compound of carbon dioxide. And so what you can probably see is that if you took the mass of the oxygen in the carbon dioxide divided by the mass of the oxygen in the carbon monoxide, what you would see is that they divide out into integral proportions. And so basically what you see is that the mass of oxygen and carbon dioxide is double the mass of the oxygen and carbon monoxide. And really the only way that can possibly happen is if you have whole integral atoms, like 1 atom or 2 atoms of the oxygen binding to 1 atom of carbon. So this could only happen if that's the case. It cannot happen if fractions of atoms of the oxygen are binding to carbon. It's not so much a case, for example, where you're having, say, 2.3 oxygen atoms binding to 1 carbon atoms. So this is the law of multiple proportions. In full form, it says when two elements A and B form two compounds, the masses of B that combine with 1 gram of A can be expressed as a ratio of whole small numbers. So let me give you sort of another example of this. So let's pretend here our element A is iron and our element B is chlorine. Now, when you form one compound of iron chloride, it's called X. You have 1 gram of iron binds to 1.27 grams of chlorine. When compound Y is formed, it's 1.92 grams of chlorine binds to 1 gram of iron. So are these compositions of these compounds consistent with the law of multiple proportions? So let's go over this on the board. So let's say we have compound X and compound Y. And so let's say we're considering the mass of iron, and we're also considering the mass of chlorine in these two compounds. And so in each case, what we've done is we've taken the mass of chlorine and compared it to 1 gram of the mass of iron. So it's going to be 1.0 grams of iron here. And then for compound X, it looks like we have 1.27 grams of chlorine bound to this mass of iron. And for compound Y, a different compound, we have a different amount of chlorine bound to the iron. It is 1.92 grams. And so the question is this data consistent with the law of multiple proportions? Okay, so what we're going to do is we're going to look at the masses of chlorine and see are these integral values of one another. And so if we have compound Y, which has the bigger mass of chlorine, we have 1.92 grams. We're going to compare it to compound X, which has 1.27 grams of chlorine. And so let's just see if these are integral values of one another. So one of the first things you might do is just divide the two numbers and see what you get. So let's go ahead and do that. So I'm going to take 1.92 grams of chlorine, divide by 1.27. And so what I get is 1.51 grams of chlorine in compound Y to 1.0 gram of chlorine in compound X. Now, what you'll see is that we don't quite have integral values, right? Although 1 is an integral value for compound X, 1.5 is not an integral value of compound Y. So the next question to consider is, can we multiply these numbers by some other integer and create integral values? And the answer is it looks like we can't. Let's try multiplying both the mass of compound X's chlorine and the mass of compound Y's chlorine by 2 and see what happens. If you multiply 1.51 by 2, I guess you'll get what? 3.02? Well, 3.02 is close to 3. If we multiply 1 gram of X by 2, we get 2. And so what you can see is in the end, we did find integral values for the masses of chlorine binding to iron. So in this case, these two compounds of iron chloride of compound X and compound Y, they do fit in with the law of multiple proportions. One thing to mention when I go over the 4 postulates of Dalton, we will find is that not all of them are exactly correct. And I will point out later which ones are a little bit off. And so let me go over these postulates. The first postulate of Dalton was that each element is comprised of tiny indestructible particles called atoms. The second postulate is he thought that for a given element, all atoms of that element have the same mass and the same properties. However, if you had a different element, those different elements' atoms would have different masses and different properties. Another postulate of his was something about how compounds are formed. He thought compounds are formed when you have different elements binding in simple whole number ratios of atoms. Finally, he suggested that what a chemical reaction is where you take a compound, for example, as a reactant, and then you have it undergo a chemical reaction, it becomes a product. And all that it happens in that process, although the mass of the compound before the reaction is the same as the mass of the compound after reaction, the only thing different, and the reason why the products are different, is because the atoms in that process rearrange themselves to form new compounds, even though the mass after the chemical reaction has not changed. Okay, so maybe the last point could be the most important and really helps you to understand how chemical reactions work. So let me just kind of give you sort of an example here. So here we have an example of some gases. And so we have oxygen in red, and you can see one molecule of oxygen has two oxygen atoms bound together. And then we have two molecules of hydrogen. Each molecule has two hydrogen atoms bound together. And so you can sort of think of that group of molecules there as reactants. Now we can force them to undergo a chemical reaction. If we hit that mixture of molecules with a spark, you will have a very exothermic chemical reaction. And then the hydrogen and oxygen atoms will undergo a chemical reaction. But look what happens. After the chemical reaction, we have products that are somewhat different than the reactants. Now, if you look at the number of atoms of each element in the products, you will find they're exactly the same as the number of atoms of each of the elements in the reactants. What has changed is that the atoms are bonded differently. And so that's what happens in chemical reactions, is that the atoms sort of rearrange each other. And so what I'm hoping you'll kind of notice is that when you react oxygen with hydrogen with some kind of flame, you create a new molecule, water. But you would expect, because there are as many atoms at the reaction as before the reaction, that you will have as much mass at the reaction as before the reaction. So another example of that is here we have two molecules of oxygen in red reacting with another molecule. That other molecule there, you can see that black atom, that is carbon, and there are 4 hydrogens bound to the carbon. If we ignite that mixture, you will have another chemical reaction. And again, what you'll notice is that you have not changed the numbers of the individual atoms of the elements. All you have done is rearrange those atoms and how they bind to each other. And so what you kind of see in that picture there is we no longer have oxygen and the carbon bound to 4 hydrogens. That molecule is called methane. They're gone. You have created new molecules, carbon dioxide and 2 molecules of water. Okay, so let me talk about now how we think of Dalton's postulates. As I kind of indicated earlier, for the most part they are true, but occasionally something is off, and so you need to know that. So I need to tell you where the postulates are a bit off. One of the postulates that he made was that all elements are made of indestructible atoms. Now, he got part of that right. It's fair to say that all elements and compounds are made of atoms. However, they're not quite indestructible. They can be broken down under certain conditions. And what I'm going to talk about in the next lecture, it is possible to strip away the electrons from the nuclei of the atoms. And so we now know that it's not too difficult to break up the atom into pieces. Another thing that he didn't get quite right was the second postulate, one of the facts in it that he proposed. He felt that for a particular element, all atoms of that element will have the same properties and the same mass. He only got that kind of part right. What he found was that if you're looking at a particular element and you're looking at the atoms of that particular element, it is true that all atoms of that element have the same properties. However, they can have different masses. And so if you're looking at a particular element and you're looking at atoms and say one of the atoms has a particular mass, the other atom has a different mass, those atoms of that element are called isotopes, and we'll talk about that later. And so the next kind of postulate he made was about the composition of compounds, and he suggested that compounds arise when elements bind in simple whole number ratios, and that is for the most part true. Okay, the final thing he kind of thought what was going on is that he thought that a chemical reaction was merely a rearrangement of atoms. That is true. However, he really did think, based on all the data he knew at the time, that the law of conservation of mass was conserved with all chemical reactions. And the fact is, with all chemical reactions, that is true. There will be as much mass after a reaction occurs as there is before a reaction. However, there is a small subset of reactions that can occur in chemistry. They are not called chemical reactions, they are called nuclear reactions. And in nuclear reactions, what can happen is that it is possible to have some reactants that react, and you'll create products with a little bit less mass. That doesn't happen very often. It's pretty rare when it happens. But if in fact the products have a little bit less mass, that difference in mass is converted to energy. So those kind of reactions, nuclear reactions, are pretty rare, and they only occur like in, say, nuclear bombs or nuclear reactors. So in conclusion, Dalton was about 90% correct, but you do need to know where he was a little bit wrong. So thank you for listening, and we'll see that.